Okay, welcome everyone. Today I am going to discuss numerical based on static equilibrium. And in this context, I have a question in which there is a sphere which is fixed between two planes. Let it be line L1 and let it be line L2. Okay. And angle between horizontal and this line is 30 degrees. So this is L1 dash. L1 dash is a line perpendicular on L1 and I have taken this line. So this is perpendicular over, let it be L3. So this is a line L3 dash. So L3 dash is perpendicular on L3. So angle between L3 and L1 here, angle between L3 and L1 is equal to 30 degree. So angle between perpendiculars, that is angle between L3 dash and L1 dash will also be equal to what? 30 degree. Now, important thing is that this is 30 degree, right? Now I am going to resolve these forces. Since this body, suppose the mass of this sphere dm, since this body is in a static equilibrium, that's why sigma fx must be equal to 0, sigma fy must be equal to 0, and sigma fz must be equal to 0. For the time being, we have taken it x-axis and this as our y-axis. Now I am going to resolve all these forces along x-axis and y-axis. So this is 30 degree. So the component of n1 in vertical direction will be n1 cos 30 degree, and component of n1 in horizontal direction will be n1 sin 30 degree. So free body diagram of this sphere is that in horizontal direction force is acting n1 sin 30 degree to the right, and from right it is n2. Since it is in a static equilibrium, that's why n1 sin 30 degree is equal to n2. First thing. Second thing is that I am going to resolve all those forces in y direction. So for y direction, this is for x direction. Now I am going to discuss for y direction. So what is happening in y direction? The component of force in y direction is, this is our body. So component of force in y direction is n1 cos 30 degree, and of course its weight will operate mg vertically downward, and component of n2 in vertical direction will be 0 because it is at 90 degree. So we can write down sigma fy is equal to 0, that is n1 cos 30 degree, this is equal to mg. So this is equation number 2, and we can easily find out whatever asked to find. Now I want to tell all of you, and I just want to give a review, is that in case of a static equilibrium, what steps you have to follow is that just to write down net forces along x-axis and equate it to 0. Exactly in the same way, write down all the forces which is acting in y direction and equate it to 0, and same with z, but here it is not required to equate 0 to z component because what is happening in xy plane for the sake of simplicity. Now I am also giving some more questions, and question number 2. Suppose there is a wall, this is a wall, and a sphere, this is a sphere, and it is connected through a string, this is a string, and it is in equilibrium, it is in equilibrium. So whenever word equilibrium comes, you have to first understand whether it is in a static equilibrium or in dynamic equilibrium. Here it is in a static equilibrium. So a static equilibrium means net force is zero as well as V relative. Body is not moving with respect to Earth. Relative acceleration is zero with respect to Earth. Now I want to tell all of you is that relative acceleration as well as relative velocity. Now I'm going to draw forces, and what forces are acting over it is that one is gravity, of course it will operate, its mass is m. Tension will act in this direction, and here normal will act in this direction. Now I am going to deal this question. So since it is in equilibrium, so of course sigma fx will be 0 and sigma fy will also 0. This question could also be solved with the help of Lami's theorem, but right now suppose this is angle theta, so of course this angle will also be theta, and its component in vertical direction will be component of tension in vertical direction will be t cos theta, and component of tension in horizontal direction will be t sin theta. So I am drawing again weight is acting vertically downward, right? This is t cos theta, this is t sin theta, and this is direction of normal. So as far as sigma fx is equal to 0, that is concerned, so normal reaction is equal to t sin theta, this is equation first, and t cos theta, that is mg, is equal to t cos theta. Okay, we can easily find out whatever asked. Next question is next type question. Suppose situation be like this. There is a ceiling, fixed ceiling, this is fixed ceiling, okay, and situation is like this. This is string, this is string 1 and this one is string 2, and a block is hanged whose mass is m. Tension in this block is T2, tension in this block is T3, and tension in this block is T1. I have assumed it. Okay, so I have also stated before you that tension in a given string will remain same. So here tension will remain T3. This is also given that this angle is theta. Now I am going to consider the equilibrium of this point. So the component, this is theta and this one is alpha. Okay. So simple procedure, since our body, our whole setup is in equilibrium. So this is in a static equilibrium. That's why sigma fx is equal to 0. Sigma fy is equal to 0. And the component of T3 in horizontal direction, component, this is T3. So component of T3 in horizontal direction is T2 sin alpha, and in vertical direction is not T2, T3. It is T3 cos alpha. Now I'm going to treat with T2. So component of T2 in horizontal direction is T2 sine theta, and in vertical direction it is what? T2 cos theta. So suppose I have assigned this point A. What is happening at this point? T3 cos alpha is acting vertically upward, and T2 cos theta is also acting vertically downward, and in downward direction there is T1. As far as horizontal direction is concerned, I am writing for point A. I have assumed this is point A. So as far as horizontal direction is concerned, now in horizontal direction it is T3 sine alpha, and this one is T2 sine theta. So of course this point is also in equilibrium, so total upward force is equal to total downward force, that is T2 cos theta plus T3 cos alpha, and this is equal to T1. And for horizontal direction, this happened for vertical direction. Suppose I took it as equation first. For horizontal direction, T3 sine alpha is equal to T2 sine theta. This is equation number 2. Now, of course, as far as mass is concerned, so weight is acting vertically downward, and of course, it is quite clear that T1 is equal to mg. So through all these equations 1, 2 and 3, we can easily find out whatever we were asked. Now I am also discussing some more question. Suppose this is two perpendicular, this is ceiling and this is wall, right? And a block is hanged in this fashion. This is M mass, and a string is also attached. So two strings are there. Support tension in vertical string be T1 and in horizontal string be T2. So now I am going to deal with this question. So as far as, since again it is in equilibrium, so what sigma fx will be equal to 0 and sigma fy will also be equal to 0. Why I am telling these things? Because it is in equilibrium. So this is T2 and this is T1. Of course, weight will act vertically downward. So for now, for sigma fy is equal to 0, that means T1 is equal to mg. This is first equation, and for sigma fx is equal to 0, I have taken this direction as x-axis and this direction as y-axis. So T2 will also be equal to 0 because in this direction T2 is acting, but there is no force in rightward direction. So of course, this is the direction of no force. So in this direction, 0 force is acting. So of course, T2 will be what? 0. So finally, we will get T1. Now I am also proceeding some new question. Suppose we have given a case is like this. This is 60 degree. Suppose this is alpha theta. This one is one string and this one is another string, and there is a block which is hanged at this point. So this is wall, and this one is ceiling. Now I'm going to proceed it, and firstly I am going to assign tension. So suppose tension in this string be T4, tension in this string be T3, tension in this string be T2, and tension in this string be T1. Now suppose this angle be alpha, this angle be alpha. Now I am telling you this angle is alpha. So the same step what I had followed earlier. So for this point, suppose this is point A, so this is point A. So in this component of T4 in vertical direction is T4 cos theta, and component of T4 in horizontal direction is T4 sin theta. Okay. Now one leftward force, horizontally leftward force is T3, and component of T2 in horizontal direction, in this direction, the component of this T2 in horizontal direction is what? I am talking about this tension T2, its horizontal direction, since it is angle alpha, so component of this in vertically downward direction will be T2 cos alpha, and in this direction its component will be what? T2 sin alpha. So one more force is T2 sin alpha, and in downward direction it will be T2 cos alpha. So we will equate this force with this. T4 cos theta is equal to T2 cos alpha, and T4 sin theta is equal to T3 plus T2 sin alpha. This is equation first, this is equation second. Now I have assumed tension in this string is T2, so of course tension will remain same, T2, and this is this was angle alpha, so of course this will also angle alpha. So this one is angle alpha. So suppose I have assigned this point B. So what is happening at point B? T2 is acting in this direction, T1 is acting in this direction, because tension always acts away from point of attachment, and in this direction, suppose I have assumed T dash, and this T dash will be, of course, will be equal to vect. So in this direction it is T dash, which is equal to mg. So now I am going to resolve these forces. To component of T2 in vertical direction will be T2 cos alpha, and its component in horizontal direction will be T2 sin alpha. As soon as I had resolved this force, we will have to remove this, because we have already resolved this force. So just write down sigma fx and sigma fy and equate it with what? 0. So when you will equate it with 0, so of course T2 cos alpha, that is equal to T dash, that is equal to mg, equation 3, and T2 sin alpha, this is equal to T1. So through all these equations we can easily find out whatever we were asked. Now some more questions could be like this. there is a man M1 and there is another man M2 which is pulling a man which has fallen. Now we have taken these are two directions and here it is M. So suppose this is next question. Now I am going to deal with this question. Since this body is hanging vertically downward, suppose this angle be theta, of course this will also be theta because symmetrical situation are there. So suppose the tension in this string be T1 and tension in this string be T2. So in this case, for this block, weight is acting vertically downward. So component of this tension in upward direction. So I am going to draw free body diagram of M. So what is happening with M? Mg is acting vertically downward and this is T2. So component of this T2 in vertically upward direction is T2 cos theta and component of this T1 in vertically upward direction is T1 cos theta. Component of T2 in horizontal direction is T2 sin theta and component of this one in horizontal direction is T1 sin theta. So this is T2 sin theta. This one is T1 sin theta. So now I am going to equate, since it is in equilibrium, so net force on this body is 0. So of course sigma fx will be 0 and sigma fy will also be equal to 0. So T2 sin theta will be equal to T1 sin theta, which suggests that T1 is equal to T2, and for this vertical direction, as far as vertical direction is concerned, so in vertical direction what forces are acting? T1 cos theta plus T2 cos theta, and this must be equal to what? Mg. So these are the way through which you can think about the question which is based over equilibrium, especially static equilibrium. So I'm going to wind it up. Okay, so today I have discussed lots of things, and in this, firstly, what you have to keep in mind is that in all cases you have to equate net force is equal to 0. You have to equate sigma fx is equal to 0 and sigma fy equal to 0, and wherever required, if required, sigma fz is equal to 0. So in static equilibrium, net force is equal to 0. These are the way to think and to proceed. Thank you so much to all of you.